Hello to all. In this section, we are still pursuing our investigation of introductory topics to Calculus 1. We will now perform completion of square and learn about the quadratic formula. This addendum to the instructional video completes techniques regarding factoring quadratic expression. In Section 5, the sum product method was introduced as a tool to factor expressions of the form ax squared plus bx plus c. But what happens if we are unable to find numbers m and n that match the product of a with c and whose sum agrees with b? Given the quadratic expression ax squared plus bx plus c, completion of squares is performed through the following steps. Step 1, we're going to factor a from the expression. Okay, I agree with you, this is not looking pretty, but keep in mind that with numbers, this will actually come out a bit nicer or easier to handle, or maybe not. We'll have to see. Step 2, divide the coefficient b over a by 2. Add and subtract the square of this term. So b over a divided by 2 is b over 2a, and we're going to add the square value of this term and subtract it right away, as you see in the blue and red terms, as to not change the overall value of the expression we started off with. Step 3, recognize that the first three terms actually form a perfect square. In fact, x squared plus b over ax plus b over 2a all squared is equal to x plus b over 2a all squared. If you want to convince yourself, you can FOIL the right-hand side and verify that it does reveal what's on the left. Therefore, ax squared plus bx plus c is equal to, we had factored a in the first place. The three terms that followed are regrouped as a perfect square, x plus b over 2a all squared. And then there is the term we subtracted to compensate for what we added earlier, minus b over 2a all squared, and c over a. Applying the square to the fraction means we're applying the square to both the b and to the 2a term, which now becomes 4a squared. And in the meantime, I've also set up common denominators for the last two terms in order to regroup them as one. Step 4 depends on what 4ac minus b squared is equal to. If 4ac minus b squared over 4a squared is 0, then ax squared plus bx plus c is equal to a times x plus b over 2a squared. And the factored form is done. If 4ac minus b squared over 4a squared is positive, then ax squared plus bx plus c cannot be factored because, in fact, we'll have a sum of squares rather than a difference of squares, which are not factorable. If 4ac minus b squared over 4a squared is negative, then x plus b over 2a squared plus 4ac minus b squared over 4a squared is a difference of squares. And in the special factored forms, we've discussed how those can be factored. Considering 4ac minus b squared is actually negative, I've factored out a sign and reversed the roles to write b squared minus 4ac. That term is positive and can be written as a perfect square. Okay, although I agreed not a pretty one. And if you remember your difference of squares formula, then you'll also remember that it can be factored into the elements that you now see in front of you. although the expressions are not pretty, we can simplify them a little bit, starting with the fact that rooting 4a squared is actually simplifiable, or can be simplified to 2 times the absolute value of a. We'll discuss why there are absolute values on the a later, but turns out that it makes no difference. If a is to be positive, then the absolute value of a will simply remain unchanged. If a happens to be negative, then the absolute value of a will require a change of signs, and then all that will happen is the terms will interchange. So in the end, ax squared plus bx plus c is equal to a times, so we had factored our a term first, and with the algebra that we've done in the last few stages, here would be the factored form. Now, this first term can be 0 as long as x is equal to minus b over 2a plus the root of b squared minus 4ac over 2a. The second term becomes 0 if x is minus b over 2a minus the root of b squared minus 4ac over 2a. Those two expressions probably ring a bell. You probably recognize what they are, and in fact it leads us to our next method, which is to factor using the quadratic equation. The factored form of the quadratic expression ax squared plus bx plus c can also be found by, first of all, finding the zeros of ax squared plus bx plus c. And the zeros of ax squared plus bx plus c are obtained directly from the quadratic formula, minus b plus or minus the root of b squared minus 4ac over 2a. Rewrite the original quadratic expression in the following factored form: a times x minus x1 times x minus x2, where, well, if b squared minus 4ac is 0, then x1 and x2, the zeros, will actually be identical and equal to minus b over 2a, which means that x plus b over 2a squared will be our factored form for the quadratic. If b squared minus 4ac turns out to be negative, then the root will be undefined, and our quadratic expression will not be factorable. In case 3, if b squared minus 4ac is positive, then the square root will be defined, and ax squared plus bx plus c will have 2 distinct zeros, and its factored form will be a times x minus x1 times x minus x2, where x1 and x2 are the zeros provided by the quadratic formula. Let's look at a more tangible example to see how these two approaches will lead to the same result. So find the factored form of the quadratic 2x squared plus 5x minus 1. So first, let's notice that there are no common elements to 2x squared, 5x, and minus 1, and therefore no simple factoring can be done. This is not a difference of squares, so special factoring forms cannot be used. And even though you may try for a while, you'll quickly realize that m and n that produce a product that match a times c and a sum that match b is impossible to guess, meaning that the m and n values are most likely irrational. Okay, so first, using completions of squares, our first step of the procedure suggested that we factor out the a term. Even though this leads to fractions, it is still part of the procedure we want to follow. So we factored 2 out from the quadratic, leaving x squared plus 5 over 2x minus 1/2. Completing the square means using half of the b over a term. So half of 5 over 2 is 5 over 4, which is going to be squared and added, as well as squared and subtracted from the expression that we have. Notice that in the second line, the outcome of x squared plus 5 over 2x plus 5 over 4 squared minus 5 over 4 squared minus a half is identical to what we had previously, just written or presented differently. In this next step, I am working on the last two fractions just to be able to regroup them. So I've created a common denominator, which is 16. 5 over 4 squared did require that we square both the 5 and the 4 in the first place. And as for the first three terms, they form a perfect square, x plus 5 quarters squared. The last two fractions put together, minus 33 over 16. So I'll just go back to the previous slide here and perhaps point out the fact that in the last step of our procedure, you've probably noticed that we are subtracting two terms. X plus 5 quarters squared minus 33 over 16 could certainly be perceived as a difference of squares. And that's how I've chosen to present it in this next operation. So 33 over 16, even though it's not a perfect number, a perfect squared number, could certainly be thought of as the root of 33 over 16 that is squared. So x plus 5 over a quarter would play the role of the a, and 33 over 16 rooted would play the role of the b in what we learned earlier as being our difference of squares formula. Okay, so with the two factored outside, I'll now apply the difference of squares formula, where x plus 5 quarters is subtracted by the root of 33 over 16 and then added with root of 33 over 16. Perhaps as a final simplification, we can just observe that the root of 16 is 4, and therefore we can simplify the root of 33 over 16 slightly by writing it as root of 33 over 4. This allows us to have 5 minus root 33 over a common denominator 4, and 5 plus root 33 over a common denominator 4. This would be our factored form of the quadratic. If you're going to use the quadratic formula, the zeros of 2x squared plus 5x minus 1, if we can find any, are obtained by applying the quadratic formula itself. The first zero we obtain is minus 5 plus root 33 all over 4. The second zero we find is minus 5 minus root 33 over 4. So we have found two distinct zeros, which are the result of the fact b squared minus 4ac was a positive number, in this case 33. So the factored form of 2x squared minus plus 5x minus 1 can be written as a times x minus x1 times x minus x2. In other words, 2 times x minus x1, x minus x2. Here are the roots that the quadratic formula provided to us. And if I distribute the minus sign to each fraction, here is a factored form for our quadratic. If you verify, you will definitely observe that this is the same result as the one we obtained by completing the square